Okay. Um, First things first. Yes, we're going to have a quiz today. Yes, you're going to have a quiz Monday. Yes, you're going to have a quiz Wednesday. Yes, you're going to have a quiz every day. Every day you're going to have a quiz until something is rectified, just so you know. I'll give you a hint. I'm looking at the situation or the lack of situation. Mm. Mm. You see that little box on my desk? When that one goes, we're in trouble. Okay, I'm just kidding. We're not. Well, I mean, we are, but we're not having one every day. Okay, first, before we start anything in class, I need to know what questions you have over 214. Say again? Number 4? Three, 4, here. After Mr. Passwater drops his latest diss track. Is that supposed to be disc? No. Diss track. Diss. Mr. Passwater's a whole lot cooler than Coach Merrick. He didn't have a clue what he's talking about. All right, anyway, it begins to get downloaded rapidly. I'm sure it does. The number of downloads in thousands T days after the disk. Oh, I see. Okay, disk track. I got you. Modeled by this logarithmic function. The table above shows the total number of downloads for this section. So here you have the days. Here you have the downloads. It's in thousands. Again, those are the type of things that you got to notice just to make sure you understand. Use the regression capabilities of your graphing calculator to find a logarithmic function. They do want the natural log. It's good because I don't think they have a log regression function, where D represents the total downloads in thousands. So you're going to have to put these in your L1 and put these in your L2. Desmos will do it somehow. I'm just not too sure how. If you guys got to figure it out, of course, you can use Desmos also. I think there's a button on Desmos you got to click to get it correct. You're nodding yes. Say it one more time. Oh, but I thought there was like a check button or a. I'll try to verify that. Yeah, log mode. Is that ringing a bell with anybody? Is anybody using Desmos on this? There's a log mode button I think you have to push. If not, your decimals are going to be a little bit off or something that I'm just going off of what I heard from somebody at one time. I haven't used Desmos on this yet. We'll get to the bottom of that. We got to figure that out before test day for sure. Okay. Use the regression capabilities. So we got L1, we got L2. You go down to regressions. You go to LN regression. Boom, done. It's going to find A. It's going to find B. And those are the only two you need because T is always a variable and D sub T is also a variable. D sub T is the predicted, and T is the value starting the initial, the value you're going to use, I guess, days. Using the model, found how many days will it take to reach 500,000? Okay, so this is in thousands. If that's 500,000, then we really just need to figure out when it's going to be equal to 500, right? And there's two ways to do this. You can graph 500. Let me kind of just, I'm not going to do it all because I don't have time to put all that in there. I don't want to put all that in there. But you have your equation now, because after you do your equation, you're going to store that in the Y1. And so that's where you guys can do one of two things. And I've talked about it before in class. I want to make sure you do know, I understand. You can do one of two things. You can go down to Y2 and put 500, or get Y1 at the end of Y1 to just put minus 500. Either way. And so if you, golly, I wish this would come up. This is so fast. And so if you put the minus 500 on Y1, then you just got to find the x-intercept. And if you put the 500 in Y2, you just got to find where Y1 touches 500. And so you're going to have to mess with you're going to have to mess with this window to make sure your Y max is at least 500. Because if it's not 500, you're not going to see that line. So that's why I just like putting the minus 500 on L1 or y1, and then finding the x-intercept. And if you don't see it, you're going to have to widen this thing out some. Really, you don't need negative 40 because you're not going to have a negative value because there's no such thing as negative days. So you really can kind of start at 0 if you wanted to. And if you don't see it, you're going to have to just make that thing big enough to you where you can see it. You can put 200,000 if you want to. You'll see it, but it's going to be so small, it's going to kind of, yeah. Is that kind of, no? Everybody okay? Anything else over that assignment? I hope that one is, I don't want to say fairly easy. It's calculator exercises, guys. You got to get used to your calculator and what it does, or get comfortable with Desmos. You just got to, because you're going to have to do one of these on the test. I mean, this test for sure, but the AP test. At least one regression. I don't know what regression it's going to be, but there will be a regression on the test. Just be careful of rounding. That'd be the only thing. Beautiful, beautiful. Find two equations. That's a common, right? Write two equations that can be used to find it, and then find them. That's like the, because this you don't need a calculator for. So this basically says, do you understand what you're plugging in values for? And then you're going to use your calculator to find the A and the B. Okay, everybody good? Happy, happy, joy, joy? No. 215. 215. I did not look at this before today. This is like a dry run. Normally I at least get here in the mornings and I look at it. I do remember 2 years ago when we did this was the very first time I ever saw it in my life. And I have a mathematics degree. So this is something a little bit different. I don't think it's difficult. Previously in 2.9, 2.9's been a while ago, we looked at the idea of using logarithmically scaled axes to help us understand data that's exponential. We now return to this idea, examine it a little more in detail through the use of what they're going to call semi-log plots. So let me remind you a little bit back in 2.9. In 2.9, we're trying to graph those things. And remember, it was so small of an increase, it was really hard to tell on the graph what those values were. And then it shoots up so quick, it's so hard to tell what they are, right? So that's kind of what they're talking about, is those graphs just do so much crazy things. It's kind of really hard to tell exactly what they're doing. You can see it, but you just can't tell exactly what the values are. So what they try to do to help fix that is do what they call semi-log plots. In a semi-log plot, one of the axes is logarithmically scaled. In AP Pre-Cal, we're only going to be scaling the y-axis. So the x-axis is still going to go negative 10, 10, whatever we decide to do. Most of the time it's not negatives, most of the time it's positives. With a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. So if you can somewhat understand that, that's pretty much what this lesson is. If you see one of these weird looking scales, so here we go. Here's the exponential graph, right? Exponential graph. Exponential, not logarithmically, but an exponential, right? It starts off at 1 million and 2 million and 3 million, and there's like, you can't tell anything about these. Like, they're going up so darn small, but really they're not going up small because it's like, that's a million. So it could go up 2,000 or 10,000 and you really can't tell. And then at some point we end up at 7 million, right? So that, again, that's what makes it difficult. And then over here, we made it 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth. Okay? All right. Previously, we looked at the two graphs displayed above using the population of English Americans in the current United States from 1620 to 1820, where t equals 0 represents 1620. On the graph on the left shows the population using a normal scale on the vertical axis. This is your XY scale that you guys have seen forever in your whole life, right? To the right is a semi-log plot where the vertical axis has been logarithmically scaled. So rather than writing whatever, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, okay? Example 1. So this is kind of what these graphs look like, okay? You're used to seeing those common growths between them. This is 10, 10 to the 1. This is 10 to the 2, 100, and 10 to the 3. So if this is 10 to the 1, I think this is actually like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then after that, it's going to 100. So now this is like 20, 30, 40, 50, 60, 70, 80, 90, 100. And then after that, now it's 200, 300, 400, 500, 600, 700, 800, 900, 1,000, or 1,000. Kind of okay? So the first group, it's going by tens. The second group, it's going by vice versa. I'm sorry. First group is going by ones. Second group by tens, then by hundreds, then by thousands, then by 10,000s. Okay? And so again, it's just a little bit different looking, but I don't think it's that difficult. Mr. Passwater, I'm sorry, that was example number 1. I skipped it. Use the features of a semi-log plot above to justify why an exponential model for the use the features of a semi-log plot above to justify why an exponential model is appropriate for the population of gross. How do you justify that that's exponential? I don't want to say it's going up very fast. The logarithmic or the semi-log plot is linear. That's how you justify it. The semi-log graph is linear. Now, it doesn't start off linear, but it kind of goes linear afterwards. A line looks a whole lot better over there than anything else. It doesn't look quadratic. It doesn't look exponential. It doesn't look exponential, logarithmic. It doesn't look quadratic. It doesn't look exponential, and it doesn't look logarithmic. It almost has to be linear. So because the semi-log plot is linear, or looks linear, I shouldn't say is linear, looks linear, then we can say that the data is exponential. Okay with that? Beautiful. Semi-log plot, how do you know? Because it looks weird, right? It starts off as like common, and then it kind of shrinks as we go. So whenever you see one like that, guys, that's a semi-log plot, okay? Mr. Passwater tells another one of his hilarious math jokes. It begins to spread throughout the school. The number of people that have heard the joke after T minutes is graphed in the semi-log plot. Even if you don't know it's a semi-log plot, they're telling you it's a semi-log plot. Where the vertical axis has been logarithmically scaled, which of the following functions could be the model for P? It ain't A, because A is linear. And what do we know about the data? It's exponential. One of the 2 or 3, and I would just kind of plug and chug. I would find a point, one that I could easily tell. 4. When I plugged 4 in, I better get somewhere close to 30. Follow? I should. If I plug in 4, I better get 30. And if I plug in 4 right here, I don't even get close to 30. Uh-oh. Guess I could turn on a writing utensil. I have to do that over here for these. No way. 4. 2 to the 4th is 16. Plus 2, 18. That's not really close to 30. Uh-oh. 2, 4. That's 2. Plus 2 is 4. That ain't 30. Well, I hope this last one kind of gives me 30. 2 to the 4th is 16. 16 times 2 is 32. Y'all okay? How do I know that? I don't know. I just plugged and chugged. And why did I choose 4? I don't know. I could have chose 5. I could have chose 3. Whatever one of those numbers I chose should go with this. I don't like to choose 0 because 0 might work with all these. So I don't like to choose 0, and I don't like to choose 1. Zeros and ones are kind of like those magic numbers because 1 to anything is 1, and 0 to anything is 0. And good? Beautiful. Important note about semi-log plots. When we logarithmically scale the vertical axis for a semi-log plot, we are not changing the y values. Duh. To logarithmically scale a vertical axis means to equally spaced values on the y-axis that are proportional, where the equal spaced values on the x-axis are linear. X is linear, y is proportional. The table above gives selected values of the function where the values of the graph could represent these data in a semi-log plot. Of course, x's are going linear, and then we're going 40, 60, 90, 135, 203. We're shooting up fairly quickly. It's not linear. Maybe quadratic. It's kind of tough between quadratic and exponentials sometimes, right? 0 to 10, 0 to 5, 0 to 5, 0 to 5, 0 to 5. It's not A. Good enough? There's no way it's A, because A goes from 0 to 10, and that data only goes from 0 to 5. 3. This is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is actually 1. I'm sorry, I keep going off 1, because this is 0 to the, 10 to the 0, 10 to the 1. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did that wrong earlier. That's 10 to the 0, that's 10 to the 1. No, none of these are under 10. Well, yeah, none of them are under 10. So I don't think it's B. What's 2? 60? 2, 50, 60. Ooh, that looks good. 2, 10, 20, 30, 40, 50, 60. Oh, that one hit it too. Yes? Find another point. 5, 200. 5, 200. 5, 100, 200. Oh no. Hit me. No, sorry. Oh, the vertical axis has to be logarithmically. And this vertical axis over here is not logarithmically. It's going from 50 to 100 to 150. It's going what? Linear. Even though it looks a little funny, but it's not, it doesn't look the shrinky things. So it has to be that one. Y'all okay? These are pretty easy, I think. These are pretty easy. I'm trying to show you the steps that when I first saw these type things, I knew there was no way it was going to be this one. I knew there was no way it was going to be this one. I knew it was no way it was going to be this one, because this one's the only type of semi-log plot. They all look like that. They all start off big and then they shrink as you get up. They all, semi-log plots, that's what they look like. So none of these three aren't even semi-log plots. Most people don't miss this question on test. Well, I'm going to tell you though, woo! That multiple choice question, dude, that's tough on this next test. Man, it's hard. Boy, it's hard. Plot the following points on the semi-log plot. Plot it. 0, 200, 0, 10, 100, 200. A, label it. Label it so I know which one it is. Don't just plot it, label it. B, 1, 25. 10, 20, 30. We're kind of like in between that. These won't have to be perfect. They don't have to be perfect. Just get them close. 2, 7. 1, 2, 3, 4, 5, 6, 7. That one you might miss because you might do what I do sometimes and start it at 0. Don't start it at 0. It's at 1. This is 10 to the 0. So this is 1, 2, 3, 4, 5, 6, 7. That one I could count you wrong. Be careful. That's C. D, oh, what the heck? 3.2. Well, that's nice. 2, 4, 6, 8. So 3.2, 800. 100. Oh, I got to pull this down a little bit. There, that's 1,000. 3.2, 100. 200, 300, 400, 500, 600, 700, 800. And that's point D. And then 4.6, 1.5. 4.6, 2, 4, 6, 1.5. That'll be counted right there in the middle because 1 is at the start and then it's 2 to get to 10. Label that one E. Good enough? Easy peasy? As we have seen, if we graph an exponential function on a semi-log plot, the graph will appear linear. In these cases, we can create linear model for the graphs of the semi-log plot. Okay, given the exponential model that, we can correspond it to that. Note the slope of the linear function is log NB and the y-intercept is log NA. The base B corresponds to the base used for the scales of the vertical axes. This semi-log plot corresponds to the data for example number 3. Write an equation for the linear model for the semi-log plot in the form of y is equal to log base NBX log base NA. Log base NA is the y-intercept. Is that what they said, right? Log base B or NA is the y-intercept. What is the y-intercept of this stupid thing? I don't want to guess. Do I guess? I told you, you're going to have to help me out on this. I didn't prep. You want to guess? It says write the equation. I don't want to guess if I want to write the equation. Use a linear model to write the equation, the exponential model for this data. Is that the last thing? Let's cheat. Let's cheat. I don't want that. I want this, this, worksheets, warm-ups, reviews, notes, 215. I hope he shows me enough. Notes, key. Let's make sure we did this right. This is example 1. The semi-log plot appears to be linear after 40 years, so the exponential model is appropriate. Good enough? Kind of what we said. That one was D. We got that right? This one was D. We got that one right. And then we did A, B, C, D, E. We got that right. Oh, I guess, no. What the heck? Oh my gosh. Jiminy. Where can I make this bigger? There. Well, I guess I can only do it once. Come on! There you go. That's a good one. Write an equation for the linear model. And for to write the equation, you need 2 things. You need a slope, you need a y-intercept. And so they found the average rate of change between 2 points, and they found it between 1 and 2. And so they said y minus y over x minus x, because those are nice clean points. And so this is 2 minus 1 on the bottom, because that's x minus x, and on top it's log of 60 minus log of 40, because this is 10, 20, 30, 40, 50, 60. So you have log of 60 minus a log of 42.1, and you got a calculator to find that value. And that's the y-intercept. Once you have the y-intercept, let's see here. Once you have the y-intercept, then we have, notice how that he does this, right? He does 0.17609 ... knowing that it's decimals that continue. X. Let me do this. Let me do this in my calculator because I want to show you guys this. Let me get out of this. Log. Now I see why they were saying what they were saying. This is my teaching friend. Log 60, careful, close it. That's log 60 minus log 40. Close it. Close it. Divided by 2 minus 1. Oh, that's easy. I didn't have to put all that in there. Good. That's that nasty decimal. If you want to leave that decimal, I know a lot of you guys go up and down, and if you need it again, you go back up there. Hit store. Store. Store it. Alpha, whatever you want. A, B, C, D. Now, every time I hit alpha A, that number's coming up. And so it's almost is a little bit easier than trying to go up and hit copy, replace, or enter. Or it's not bad. It's just a little bit of a quick step. Okay, you'll kind of follow that. Click, 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 click. Where am I at? I'm here. Okay, so then I have to find the y-intercept. I'm sorry. Yes, the y-intercept, because we don't want to guess. And so we find the y-intercept algebraically, because you now have the slope and you have the, you don't have the y-intercept, but you have the slope and you have a point. So once you have the point and once you have a slope, you can find the y-intercept algebraically. It's just like y equals mx plus b back in the day, except you got some weird numbers, right? But you have the 2 points, so you can use either point. You can use the 1, what did we decide? 160, 140, or the 260 to find it. But it's log of 60. It's not 60 by itself. Using the linear model from part A, write the equation in exponential. So here's where they say, y'all okay with A? Y'all good? You okay? In B, using the linear model from part A, write the equation in exponential model, y equals A times B to the x. And so A is 10 to that 1.4 over here. Boom, 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 boom. And that's whatever, 2.6 repeating. Again, this is where you might want to store these values. B is that. You have, this is where you got to go back. You have y equals A, B to the x. And you got an x value and you got a y value. And you got another x value and another y value. You just have to find A and B. Okay, you have 2 x values, you have 2 y values. So plug in the 2 x values and plug in the 2 y values and find A and B algebraically. Because anytime you have 2 equations with 2 unknowns, you can find the 2 unknowns. I hate that I'm not walking through that with you, but hit me. What is with the 2 equals that? This? I don't know. Oh, that's times 2. That's the x value. He used the x value. He used the 260. I would have used the 140. Are you with me? No? Yes? You're not. It's okay. N, right? A, B, plus times x, plus, okay? And here's where you have 1 log 40 and 2, log 60. And if you have 2 points and 2 unknowns, you can write the equation of the line. So plug this in for y and plug this in for x and plug this in for y and this in for x and find A and find B. Okay? And then you have 2 more equations. Plug this in for y, plug this in for x, plug this in for y and plug this in for x and find A and B. Yay? You guys know how to do that. You got calculators. Calculator. It's mostly calculator. It's mostly calculator exercises. It's mostly calculator finger exercises. Use the store button. Don't round, don't round, don't round until the very, very end. Don't round until the very, very end. That's why I think you probably ought to use a store or go up there and hit those enter buttons or whatever you got to do. Store is a little bit quicker. Everybody okay now? Hopefully that clears it up. I don't want to do it because I don't want to punch up my fingers. You guys need practice. But if you need help on Monday, you will ask. What's today? Friday, right? Monday. So Monday we're reviewing. I'm going to give you the review today. So I'm giving you 215 and the review today because the review is long, but it has to be because this is a long unit. Some of the sections were pretty easy. I think this section's pretty easy. I think that's a hard question, but I don't know how hard it is. But most everybody does fine on it because I don't think we asked this one. 213 is brutal. 213 is brutal.